This is problem 1353. It's on page 723. The volumetric analysis of mixture of gases, I think of a mixture of gases, is 30% oxygen, 40% nitrogen, 10% carbon dioxide, and 20% methane. Wow, that's a mouthful. We might want to note this as we go. So what are we given? The volume, the volumetric analysis. So the volume of the oxygen divided by the volume of the mixture is 0.3, which, by the way, this is just the mole fraction, right, because of Amagat's law. And the volume of the nitrogen divided by the volume of the mixture was given as 40%, and that's not just y sub I, that's YO2. This would be YN2. And then the volume of the carbon dioxide over the mixture volume is 10%, so YCO2. And finally, 20% methane. So volume, instead of writing M I'm reserving for the mixture. I'm going to write CH4, the chemical formula for methane, since it's short and easy to write. So this is Y of CH2. All right. So I wanted to jot that down because that was quite a bit. This mixture is heated from 20 to 200 degrees Celsius while flowing through a tube in which the pressure is maintained at 150 kilopascals. So they've got a figure for us. I guess I'll put it down here. A piece of pipe, something like that, with flow coming in one side and leaving out the other, heat transfer coming in this way. Where it begins, well, I mean, the pressure is just constant at 150 kilopascals, but the temperature begins, if we make this state 1, T1 is equal to 20 degrees Celsius. We'll make this state 2 at the exit, so that T2 is equal to 200 degrees Celsius. But while flowing through a tube in which the pressure is maintained at 150 kilopascals, determine the heat transfer to the mixture per unit mass of the mixture. So, in other words, we do want little q because that's heat transfer per unit mass. All right. So the change in temperature is obviously just 180 degrees Celsius. And I think the difference in temperature is the only thing we'll need, so I'm not going to bother with trying to figure out the absolute temperature. I don't think we'll need that. I'm going to basically just write an energy balance. That's the only tool I know of that will do this. So an energy balance around this section of pipe just says heat comes in and it increases the fluid power. And it would end up looking like this: Qn equals H2 less H1. Remember, these are flowing streams, so they have internal energy and flow energy. That's why we have to use enthalpy, because that accounts for both. So we've got internal energy and flow at the exit, internal energy and flow at the entrance. Now, I don't really want to use enthalpies because I don't have a table of enthalpies for this unique mixture of gases. What I would rather do instead is say this is approximately the heat capacity of the mixture times the temperature change of the mixture, T2 minus T1, which is what I've got here at 180 degrees. So I've almost got it, right? Because the temperature change is no problem. All I really need is the heat capacity of the mixture. Now, the heat capacity of the mixture, to get that, since it's a per unit mass thing, I'm going to need to add all of the mass fractions and multiply them by the heat capacities of all the different species. And unfortunately, I don't have the mass fractions, I have the mole fractions instead. There is a relationship, though, between mass fractions and mole fractions. It is as follows. I just need the molecular weight of the mixture. Don't have that either, so how could I get the molecular weight of the mixture? Well, fortunately, the molecular weight of the mixture is pretty straightforward. All I need is all of the mole fractions times the molecular weight, or the molar mass, of each species. And I think I wrote this wrong because I wrote M sub m here. I need to correct that. It should be M sub I. So this is pretty easy. All I need to do is take 30% of whatever the molecular weight is, or the molar mass of oxygen, 40% of the molar mass of nitrogen, and so forth. So I looked all of these up, and for oxygen, O2, it's 31.999. I'll write the units at the end. or I'll be writing them all day. 40% for the nitrogen. Well, nitrogen's molecular weight is 28.013. Then 10%, the molecular weight of carbon dioxide, but carbon dioxide's molecular weight is 44.01. And then 20% of the molecular weight of methane, 16.043. And these are all kilograms per kilomole. Okay? So that applies to all of this. So now that I have an equation for it, I guess I should plug it into a calculator. When I did that, I came up with 28.4145 kilograms per kilomole. Now that I've got that, I can figure out all of the mass fractions. So for example, the mass fraction of oxygen would be equal to the mole fraction times the molecular weight of the oxygen over the molecular weight of the mixture. And so that would be 30%. I just need the molecular weight of oxygen. I've got it. By the way, this is the oxygen. This one is the nitrogen. This is the carbon dioxide. And the last one should be methane, CH4. So for the oxygen, the molecular weight is still 31.999. Let me change this just a little bit. 31.999 divided by the molecular weight of the mixture, 28.4145. Both of these have the same units, so won't bother writing them in. And the mass fraction will come out dimensionless, just like the mole fraction is dimensionless. So when I did this, I came up with about 0.3378 as the mass fraction of the oxygen. Now I can do the same thing over and over again for the nitrogen, carbon dioxide, and the methane. I'm running out of space, so I'm going to do it down here. But I'm going to do it a little more quickly. The mass fraction of the nitrogen would be the percentage of nitrogen in terms of molar percentage, YN2. And instead of writing that, I guess I'm just going to plug in numbers. So 40%, I need the molecular weight of nitrogen, so that's 28.013, and I need the molecular weight of the mixture, 28.4145, and so this comes out to a mass fraction of about 0.3943. Okay. The mass fraction of the carbon dioxide would then be 10%. The molecular weight of carbon dioxide, 44.01, divided by the molecular weight of the mixture, or apparent molecular weight of the mixture. Plugging all of this into a calculator, we come up with about 0.1549, 49, as the mass fraction of the carbon dioxide. Finally, the mass fraction of the methane, CH4, would be 20%, which is the mole fraction, times 16.043 by 28.4145. That comes out to about 0.1129. And now finally, I can plug all of this into my equation for the heat capacity. I just need the heat capacity of each one of these. So I'm going to need the mass fraction. I guess I'll write it out. I'll need the mass fraction of oxygen times the heat capacity of oxygen plus the mass fraction of the nitrogen times the heat capacity of the nitrogen plus the mass fraction of the carbon dioxide times the heat capacity of the carbon dioxide plus the mass fraction of the methane times the heat capacity of the methane. Okay. It's kind of long, but there it is. I think I can sneak it in here. So this is going to be equal to mass fraction of oxygen. We've got that now somewhere. Here it is, right below me. So it's 0.3378. That's the mass fraction of the oxygen. The heat capacity of the oxygen you have to look up. And I won't write in the units for the heat capacity of the oxygen or any of the heat capacities until the end. So 1.7113 is the number I've got. It will end up being in kilojoules per kilogram per Kelvin, but as I said, I'll reserve that for the end. And then I need the mass fraction of the nitrogen, that's right here, 0.3943. And then the heat capacity of the nitrogen, but that's just 1.039 kilojoules per kilogram per Kelvin. And then the mass fraction of the carbon dioxide, 0.1549 times the heat capacity of the carbon dioxide. When you look that up, it's 0.846. And then the mass fraction of the methane, 0.1129, times the heat capacity of the methane, 2.2537. These are all kilojoules per kilogram per Kelvin. Okay? Plugging all of that into our calculator, we'll find that the heat capacity of the mixture, I guess I should have just written it up here, I'm going to use it here anyway. The heat capacity of the mixture, this long number, comes out to 1.373 kilojoules per kilogram per Kelvin, so 1.373 kilojoules per kilogram per Kelvin, times the change in temperature, which is 180 degrees Celsius. It's temperature difference, so that'll cancel just fine. Plugging all this in, this comes out to about 247.18 kilojoules per kilogram. So there's the heat transfer per unit mass required in order to heat this mixture from 20 degrees Celsius up to 200 degrees Celsius.